Okay.
Yeah, first of all, we have audience, people, mix of technical and non-technical, fair amount of technology people here. Therefore, feel free to be technical on the conversation, and wherever you can generalize will be great. Just want to quickly introduce Abhishek. Abhishek is actually, I would say one of the well-known data scientists in the world. He's highest rank of world number 3 in Kaggle. He's also our advisor on the board. And first of all, thank you for taking time on your weekend, Abhishek, to be on this call. And not only people in this room, this is live telecast, and also we are going to share this link, the YouTube video, to thousands of people who would be interested in this. So thanks once again for sparing your time, and look forward to a very productive session. And over to you.
Thank you very much for inviting me. So, is it possible for you to switch off your microphone?
Yeah, done.
Okay, great. Okay, so thank you very much for inviting me and for the introduction. So, I'm going to talk about approaching almost any machine learning problem. The talk is a little bit technical, so if you're from non-tech background, then feel free to ask at any time, and I will try my best to explain. So about me, I currently work as Chief Data Scientist at Boost AI, which is a company based in Norway, Stavanger. It's a small city. And few years ago, I was ranked number 3 on Kaggle. So I'm quite active during in the discussions, and also taking part in almost all competitions which are going on. So you can see, like, I've taken part in almost 150 competitions. So when it comes to approaching machine learning problems, so what we are going to discuss is maybe quite basic for you guys. So, like, types of machine learning problem, what are the different kinds of evaluation metric, what is cross-validation, how do you handle categorical data, handling numerical data, text data handling, images. We are not going to do that because you are already dealing with images in your everyday job. And look into some hyperparameter tuning. So to start with, we have supervised and unsupervised learning, right? And what we have here is, like, different samples which are in different rows, different observations, and we have different features for each of the samples. And then there is a target variable. Let's say probably this is binary, true or false kind of variable. So this kind of problem is a supervised problem. Just like, so if you take any kind of basic problem, like even in your day-to-day work when you're tagging images, so that's mostly supervised. And unsupervised problem would be something like fraud detection problem, where you don't have these targets. So suppose there are many transactions and you want to detect what kind of transactions are fraud transactions. So what we do in unsupervised is basically clustering kind of approach. So the problem with unsupervised problems is there's still a lot of research going on there, and the results are not so good. So people tend to avoid those kind of problems which are unsupervised, especially me. So what you do here is, like, you do a clustering, and then you can see some of the samples are red in color, some are green. And when you cluster them, so you can see some kind of separation, which is not always there. And it becomes very difficult for these kind of models to generalize. In the next one, so the problems can be divided into classification or regression kind of problems. So in classification, you are predicting a class or a target variable, which is discrete. And in regression problems, you are predicting continuous values. So these are the classifications for supervised kind of problem. And what are the different types of classes or targets that we can have? So one of them is a single column binary values. So you have a classification problem. One sample belongs to only one class, and there are only two classes, true or false. You can also have a single column real value problem. So you have a regression problem, prediction of one value. So let's say you're trying to predict the price of certain product in next month. Or you can have multiple column binary values, which is classification. So one sample belongs to one class, but there are more than two classes. So some kind of product classification where you have a lot of products. And you have multiple column real values, so it's regression, but different targets. And multi-label problem. So multi-label it's also a classification problem, but here one sample can belong to different classes, many different classes, or just one. So it's like fashion images, where you have multiple attributes associated with one image. There are many different evaluation metrics, and people tend to get confused quite a lot. So there are some accuracy which is probably quite easy to understand. Then you have absolute error, root mean square error, log loss. AP at k is average precision at k, and there are many more. So this tends to get a little bit confusing, and what I think is there are few evaluation metrics which are good for classification problem, and they are accuracy or log loss, F1, area under curve, which is very widely used on Kaggle competitions and also in real world. And then we have for regression, I think we are mostly interested in the top two, MAE or MSE, or sometimes R square. So once we have a little bit of understanding about different metrics, we can move to some data. So let's take a look at this data. So we have like 5 columns and many rows, and what do we see here? Like the first column seems like it's only ones and zeros, and then others have just numbers, large numbers. So what we do is we do a simple value count. So I love pandas. I use pandas a lot. It's quite easy. And a simple value counts for the first variable shows me there are 30,000 samples for 1 and 1897 for 0. And it probably looks like a target variable, and it is target variable. So when we come to first variable, we see the values 4, 6, 7, 5. This is repeated more than 800 times. Other one is more than 400 times. So it goes down till 200. So it seems like a categorical variable. So what we do is when we are handling the categorical data, we have the categorical features, so we can do different kinds of things. We can just do no processing at all, just feed them to some kind of machine learning algorithm without any processing. We can do frequency encoding, we can do one hot encoding, and we can also do label encoding. So to look at that, you say like we in no processing there's nothing. So in frequency encoding, you replace them with the frequency counts. One hot encoding is more of like embeddings, binarization kind of thing, and then you have label encoding. So you replace every categorical feature with a integer. But when you look at the data further, the same column, you see like there are many values which are occurring only one time or less than 100 times. So some values are omitted here. So what you can do for these kind of data is to put them in a rare category. So you have this feature, and you can just do a group by on the feature and then see what is the length of the group by. And so this is wrong here. It should be 100 and 100. But if this is less than 100, so we just put it in a different category and call it a rare category. Just a second. Okay. So anything that is less than 100 times is converted to a rare value category. Now let's take a look at some other kind of data. So again, you have like 4, 5, 5 columns, and you can see like just by looking at this data, you can say like first 2 columns are categorical and the rest are numerical columns. And to handle this kind of data, you obviously first have to read the data, and Pandas is quite fast with that. What you can do is you can process these 2 different kinds of features differently. So for one of the features, which is categorical variable, you can use one-hot encoding. So you can define what different categorical variables you have, and you can transform those to one-hot encoding matrix. It would be a sparse matrix. And for numerical features, you don't have to do anything at all. So you can keep it as it is. So once we have done that, we are in the process of building the whole pipeline for solving these kind of problems, or for solving problems in general. So first of all is the identification of different kinds of variables, and then you stack them together. And in the end, you have the matrix that I have shown before. So you have different features and different samples and the target variables separated from each other. Once you have that, you can either process them, like if you just have numerical variables, you can scale them, or you don't need to scale them. When you don't need to scale them, you can use algorithms like XGBoost or LightGBM or any tree-based algorithms. But for most of the algorithms, you need to scale the data properly. So what you can use is something from scikit-learn processing. You can use standard scaler, which is JASCO scaling, min-max, which is scaling between a minimum and maximum value. And you can also use robust scaler, which takes care of outliers. And then we have, for a classification problem, different kinds of cross-validation techniques. So it's very, very important to build a good cross-validation. If you don't have a good cross-validation, probably you're getting very good results locally, and when you put things in production, everything fails. So for classification problem, you can use different kinds of cross-validation. So let's say the first one is k-fold. That's very simple. You just divide the data randomly into training and validation sets. Another one is stratified k-fold. Stratified k-fold takes care of the percentage of target variables. So if you have a binary classification, the ratio of ones and zeros in every split will be the same. Then you have leave one out cross validation. So that's typically done when you have very less number of samples to train on. So you just leave one sample out, train on everything, and then test on one sample, and you repeat this process for the number of samples you have total. And then you have leave one group out. Now that's an interesting one. What you do here is, let's say you have another variable which is in training data, and in test data that's entirely different kinds of values for that. So what you can do is you can group by this variable. So in every split, you will have in every split in training and validation, you will have you won't have any groups, any kind of values from this feature which are in training data. For a regression problem, you don't have stratified k-fold, so you have simple k-fold, leave one out and leave one group out. You can build stratified k-fold on your own if you want to. So for that, you have to make sure the distribution of target variable is same in training and validation sets. So when we are trying to put it all together, what we have is we define the number of folds we want to use, some kind of random state to initialize random seeds. And here I'm just making the code read what is the model name based on the script name and the number of folds. So when you have that, the next thing to do is to get the target variables, read the training data, training and test data, and then get the target variables, remove the ID columns if there are any, and then transform test data to the same features as training data. So they should be in the same order. And here, the data is probably just numbers. So I'm just making everything as type float. And then from scikit-learn, you have stratified k-fold, and you can have different splits, and you can generate out-of-fold predictions and test predictions for every fold. So I'm just initializing these vectors here. And then for each fold, you have training and validation indices. So you get the training and validation data from there. You define whatever kind of model you want to use, and then you generate predictions for validation data and for test data. And you calculate the metric that you have chosen earlier. And you put the validation predictions in the out-of-fold predictions and test predictions in the test predictions. And in the end, you divide by the number of fold for test predictions. You just take an average. And that gives you a quite good model. So it's very necessary, like data science, that the code should be reproducible. It's not most of the times. And that's because we tend to experiment a lot and not save every experiment. So what I usually do is just save the source code that generated that score. And you should actually probably do it in the very beginning. So when we're putting it all together, we have data. So we do the data munging. We have converted into features and targets, build a cross-validation system, and in the end, you have a model which should probably be good. So after this, there are many different ways to handle categorical features. And one of them that I'm going to talk about right now is called entity embeddings. So when we talk about word embeddings are converting every word to n-dimensional space vector. So every word can be represented as vectors. Similar is for categories. So every category can be represented as vectors. And so if we take a look at this data, we have the ID column and the target column separated from each other. Then we have some version numbers. And we see that, like, if we do some initial exploration, these are all categories, or can be treated as categories. So what we do is we read the training and test data, get the target column, and then how I'm checking if the unique values in every column is less than 15,000. So you can choose any kind of threshold you want. The column is usable as in I'm going to treat that column as category. And then what you do is you encode them into integers, starting from 0 to n. N is the number of categories you have, number of unique values you have for every column. After you're done with that, it's a very simple thing to then just to build entity embedding model, and then you have model and all the columns. So how it happens? You split the training data in training and validation sets. And so here I've just taken like 90% of training data. So it's a bad way of doing it, but sometimes it works. So it's just a holdout. And then I fit it using a generator. So I'm using Keras. So we can create a generator for the training data and also for the validation data. So you can choose the number of steps you want. That's it. It should be equal to the number of samples you have divided by the batch size, or you can train more. The number of epochs you want. And after that, the building block, which is the creating the entity embedding model. So you take all the unique values for a column and create a embedding vector, and that vector is so I have taken like it should be number of unique values, half of that, or the total number of, or 50. So between that, whatever is the minimum. Then I added a spatial dropout. So in the end, you append all these embedding vectors to your inputs, and your output is just one value. So when you have all these inputs appended, what you can do is you can concatenate them and add some dense layers to it. So inputs are these vectors and output is a single value. So writing a data generator is a very easy process, and I think people should write more data generators, and when they're pushing models through production, especially when you're dealing with a lot of data and you want to like even train online. So it just requires the data input, which here is a pandas data frame. Then you have the columns, which are the required columns, certain batch size, and if you want to shuffle it in every batch. So using the batch size, you decide what are the total number of batches, and then you just write a generator, so which takes the batch index, which indexes to use for this batch, and according to that, select X and Y, and keep increasing the counter. So counter is here because you can you might want to use it for some other purposes. So if the counter is equal to the number of batches, you can just break. And what I've done here is to convert so this is my input and this is the target variable. So everything is a list of columns. So The many different ways include label encoding them, converting to numbers, one-hot encoding, and making them binary. You can also convert to counts. So group by take the counts. And converting to embeddings, I've used TensorFlow or Keras. You can also create more categories based on the categories you have. You can divide one category into several categories. And you can use factorization machines for categorical data. The next thing that we come to is feature engineering for numerical features. So you can have different kinds of transformation, log transformation, exponential transformation. You can have some kind of binning. So here I use pandas cut, and it divides into 100 bins and returns the bin number. So you can just add the bin number for every value, or you can create some kind of interaction. So I'm going for very basic polynomial features, which generates interactions like this. So this is also from scikit-learn, and it will generate for any two variables. It will be a and b. It will generate a square, ab, and b square. And if you include bias, then also a 1 with it. Then you have to select the best variables. So you can do some kind of recursive elimination of the features. So you train a model on certain set of features and then remove one feature, train the model again, and see how the score drops or improves. You can do some kind of mutual information based selection and chi-square. So that's mainly used for text data sparse matrix. But selecting features I think this is also a question about feature engineering. So it doesn't matter how you select those features. You have to see to make sure feature selection works. It's like throwing spaghetti on the wall and see what sticks. So you keep training a model with new features that you have added, and if your model is improving, then it's a good feature. There is no other way to generalize this. So there are many situations where we don't get data in a tabular format. So here you can see this is tabular format with card ID and target column, and you have certain features. One is date. But for every card ID, you have a lot of metadata. So here you can see only one card ID is present. So in the previous slide, I've shown you there are many different card IDs, but for every card ID, you have some other values. And that makes it very difficult. So in these cases, what's required is to aggregate for card ID and create features based on different values that you have here. How you can do that using pandas, it's quite easy. So here I'm just converting year to here I'm just making features like year, week of year, month from a date column, and then you define what kind of aggregates you want to use. So like you want to use aggregate for the column month or column hour, and what kind of values you want from it. So number of unique values, mean, or like from purchase amount, you want to have total purchase amount, maximum, minimum, mean, or variance, these kind of things. And card ID size is like how many times they have done certain transaction. And these aggregate features can be created quite easily using pandas. So you have you group by the card and then create aggregates of these features that you have defined here. And that gives you a lot of different kinds of features. And you can also create features like skew kurtosis. You can create percentile-based features. And if you're using pandas, then that's also quite easy. So here you can see, like, I have added for purchase amount, I added a quantile feature. So I have to define that feature on my own, but I can just write the function name here, and pandas will take care of everything else. So moving on, what happens when you have only like one feature? So this is an ongoing Kaggle competition. So you have some kind of acoustic data and time to failure at every sample. So there is basically only one feature, acoustic data. And it's a regression kind of problem. So training set is a one large file with 2 columns, and test set is a different files with 150,000 rows, with only the acoustic data column is present in the test set. So yeah, but if you don't have any data, probably you cannot build a model, but that's not true. When there is just one feature, you can build some kind of generator using pandas that gives you chunks of 150,000 just because your test data is 150,000. And here x for every iteration in this loop, x is 150,000 and y is only the last value that was seen, and that gives you a smaller data set. Not smaller, but you have less y value, less target values. So first step is to divide it into chunks. The next step is to create features based on these chunks. So a feature can be mean of the chunk, or max, standard deviation, peak to peak. And you can also do something like you can count ever mean, the total amount of energy, or mean change. So for this, you can use something that I found very interesting for creating time series based features. It's called TS-Fresh. And you have more than hundreds of time series based features there. And you can also take a look at this link, which is here, to and provides you with the whole source code for this, and I think more than 50 features. Okay, the next thing that I would like to discuss is when there is no numerical feature. So when you have data that looks like this, and you can see like the first 3 columns are ID columns, so we can probably ignore them. So you have a question 1 column, question 2 column, and is duplicate. So here you can see only zeros, but probably there are also ones. So the problem statement here is to find out if questions are similar to each other in these 2 columns. So if the person is asking the question in the same way, not similar way, and to handle this kind of data, you can come up with very basic features like what is the length of question 1, length of question 2, what is the difference in the 2 lengths, the character length without spaces or character length with spaces, the number of words, the number of common words. So this will give you a very basic set of features. And they can be created very easily. So you can just use lambda functions and pandas apply to create these kind of features. So you have, let's say you have length of word. So you just split by all kinds of spaces, and then calculate the length of that list and just return that value. So or you have common words, so you can just take words and convert them to sets and get the intersection and calculate the length of that intersection. So after creating the basic sets, we have something called fuzzy features. So fuzzy features are also called as approximate string matching. So you have different kinds of operations like insertion, deletion, substitution. So what kind of primitive operations you can perform to convert string to an exact match? So they are typically used for spam filtering or spell checking. So you can create a spell checker based on fuzzy features. So that's there's a there's a Python package called FuzzyWuzzy, which provides a lot of different kinds of fuzzy features for text, and it uses Levenstein distance. And again, by using pandas lambda and apply, apply function with lambda, you can create these features quite easily. So like here, I've created Q ratio, W ratio. So I'm just taking a bunch of different kinds of features from this FuzzyWuzzy package. The next thing that you can do quite basic is TF-IDF. So, so TF-IDF consists of two different terms. Number of times a term T appears in document divided by the total number of terms in the document, which is the term frequency, and log of total number of documents over number of documents with a term T in it is the IDF for a word, for a term T or word T, and then you multiply them, you have the TF-IDF. And this is from scikit-learn. I use it everywhere. This is like my first step for any NLP problem, and I just use these parameters, and they always work. Probably need to modify stop words from English to something else, or don't use any stop words at all. The next thing that you can do is you can do some kind of decomposition on the TF-IDF features. So here I'm using a variation of SVD known as truncated SVD, and I used 120 components. You can start with very small number of components like 60 or 30 and move to 120, 180, but more than that, it doesn't even matter that much. Yeah, it's also known as LSA, or latent semantic analysis. So you can use it in many different ways. So let's say you have question 1, you perform TF-IDF only on question 1, and you have question 2, a separate TF-IDF on that, and then you have a machine learning model. Probably you concatenate these two TF-IDFs, and you can build a machine learning model, probably just simple logistic regression. Or you can combine these two questions together and then build the TF-IDF matrix and the machine learning model. So another way would be to decompose this TF-IDF matrices individually and stack the matrices, SVD matrix together, and then build a machine learning model. So probably you can go for random forest or XGBoost here, some kind of boosting algorithm, or to just combine the TF-IDF and then do a single SVD. And one more way would be to do something like this, where you combine the question, you have the TF-IDF, SVD matrix, and then the machine learning model. So once you have all these basic features, we can move to something more interesting, like word-to-vec features. So what word-to-vec does is you have multidimensional vector for all words in any kind of given corpus. So mostly usually provide with quite good insights, and one of the oldest one is Google News vector, and they're quite popular in natural language processing tasks. So it works something like this. You have a vector for different cities and countries, let's say, and you have vector for Germany, a vector for France, vector for Paris, and vector for Berlin. So if we subtract the vector for Germany from Berlin and add France to it, we get the vector which is very close to the vector for Paris. Yeah, so, and this kind of thing can be used in natural language processing in different ways. So one way is to just represent sentences instead of representing words. So you can do it very easily. So let's say you have a dictionary or model, which is a dictionary of words and these vectors. So you can take every word from the list. You can apply some processing to it. I'm using NLTK's word tokenize function here for tokenization, and I'm removing all the stock words, and I'm checking if the word is alphanumeric. For all the words, then I add them to, I get the vector from the model, and I add them to this list, and I convert that list to an array, and I just normalize it by the square of counts. So this function I've used before, and it's doc2vec is also something that you can use, but for me, this has always been more useful than doc2vec. It's quite simple, and you can also create a lot of different kinds of features from word2vec. So remember, we have like 2 questions. So for each question, you have these word2vec sentence to vectors. And using a SciP, you can calculate different kinds of distances between them. You can also have some more statistical features like skew, kurtosis. You can keep on adding as many features as you like from scip.stats. And other features based on word2vec is word mover distance. So if you look at these 2 sentences, Obama speaks to the media in Illinois and President greets the press in Chicago. Now there are no common words. So the cosine similarity will say that these 2 are not similar to each other. But you can use word mover distance, and that will give you, for every word it says, what is the distance to move from one word to another, and then it will give you like a score, a similarity between these 2 sentences, which is not possible using conventional methods. So in the end, we have created a lot of different kinds of features. And here is this snapshot for one of the samples. So you have length of Q1, Q2, and some fuzzy features, number of common words, and then you have to have some kind of machine learning model on top of it. So the machine learning models specifically for this problem, when I tried it, I used logistic regression and XGBoost, simple 5-fold cross-validation. I use accuracy as a comparison metric, and a lot of people would say, why accuracy? We could have used AUC. So the only reason of using accuracy was the data comes from Quora, and when Quora released the data, their engineering team wrote a blog post and they use accuracy as a metric. So I use accuracy as a metric just to compare with them. So I tried these 2 different models, logistic regression and XGBoost, on different sets of features. So just on the basic feature, logistic regression gives about 65.8% accuracy and XGBoost 72.1%. So we see like there was a very large feature set that I didn't even bother training logistic regression with. I didn't have enough memory RAM. And XGBoost accuracy was 81.4%, which is the highest among all these. So that's quite satisfactory. But it's the era of deep learning. So everyone is talking about deep learning, so we should also use that. So for deep learning, I used LSTMs, so invented by Schmidt-Huber. So I used 2 LSTM layers, and the problem with LSTMs is it takes a lot of computational power, and you can have some simple layers like one-dimensional CNN, which is quite easy to implement, kind of temporal convolution. So I use that, and embedding layers. That embedding is something that we have already discussed before. So embedding layers are just converting these indexes to vectors. I also use time distributed dense layers. So written by it's similar to Keras SNLI model. So it implements a translation. So I have time distributed on the dense layer, and before that I have the embedding layer, obviously, and then a lambda function which takes a sum. The embeddings, you can use some pre-trained embeddings like Glove or fasttext. In this specific problem, I use Glove embeddings, and the Glove embeddings have like 840 billion tokens and 2.2 million words. These are 300 dimensional. But to handle text data, it's done in a little bit of different way than other kinds of data, like image or other numerical data. So we define a tokenizer, and we define, so everything here has been done using Keras. So I choose a max len of 40, which is the number of words I want in every sample. After that, I just truncate, and you fit the tokenizer on these two questions that you have and convert them to sequences. Now these sequences are just numerical representation of the words. So every word gets an index, and that index appears in these sequences. And then we have to pad the sequences. So let's say if some sentence is less than 40 words, we just pad it with zeros, make it of the length 40. And then you have the word index. So word index same, you have word, and every word has an index. Then you need to initialize the Glove embeddings, so which is nothing like rocket science here. So I just open the file and I read every line in a dictionary. So the first column in this file is the word, and everything else is the vector for that word. So I just read it in this embeddings index. And then you create the embedding matrix. So you take all the words from the word index that you have created already. And for every word, you check if the word is in embedding index, then you get the word. If the word is not there, if the word is not, if the vector is not none, then you put it to embedding matrix. Otherwise, you just assume that it's all zeros. And this was the final deep learning model that I used for this problem. The problem with this model is it's huge. So we have to break it into different parts. So let's take a look at these two models first. They look something like this. So something that we just discussed, a time distributed dense, and I take the weights from the embedding matrix, and I make the embeddings non-trainable. So you have the input layer, embedding, time distributed dense layer, and a lambda layer. The second and third, second pair of inputs is a convolutional model. So you have the embeddings, one-dimensional convolution. I added a max pooling layer, some dropout dense layers. So you can do the same thing in Keras very easily. And here also you can see like the embeddings are non-trainable, and you can have a bunch of convolution layer. I have just one. The third pair is simple LSTMs, And what I did differently for LSTMs was I didn't use any pre-trained embeddings. And in the end, I just merge all the layers together, add a batch normalization, and a bunch of dense and dropout layers. So it was a huge network with 174 million parameters. I used Titan X at that time for solving this problem, and then I was just waiting for this network to train because it takes a huge time to train on Titan X. Probably now it's faster. So 15 hours, 10 to 15 hours for one epoch, and it achieved an accuracy of approximately 0.85, which was more than XGBoost or logistic regression. And the thing is, this accuracy was also very close to what the state-of-the-art result was at the time, which was something very complicated. So you can see, like, you can build different kinds of neural networks and try different kinds of things, and probably you will get state-of-the-art result without even diving very deep into it. And like for a production environment, I don't know if there's a huge difference between 85% and 88%, because I mean, as long as it's not financial firms and stock market trading. But you can be more creative with text data. So you can have you can apply some kind of language detection, cleaning up of. So for language detection, you can use pre-trained models like from fast text, or there's a very simple one called LangID. Or then you can apply some kind of cleanup, which is quite necessary even for neural networks. And then you have tokenization. So tokenization means like splitting a sentence into different words, but that becomes a little bit complicated when you have, let's say, Chinese characters. And then you have stemming, in which you reduce a word to their base form. So if you have words like fishing, fishes, they all get reduced to fish. Then you have synonyms and stop words that you have to take care of. So a very simple way to augment text or data would be to replace words with synonyms randomly. So you can try something like that. And there is a thing like sometimes stop words are useful, sometimes they are not. So it totally depends on your problem. So I deal with virtual assistants, and I have seen stop words are quite useful to us because it changes the meaning of the sentence. And then we have spelling correction. So for spelling correction, I have already mentioned, like, you can use some kind of fuzzy distance to calculate. You have a list of words, and you can, yeah, if you get a word, you can just calculate some kind of Levenstein distance, edit distance, not Levenstein distance. That's a variation of Levenstein. You can use that for correcting the spelling. So compound splitting is something interesting. Compound splitting is like when you have very bad text data, like let's say from Twitter or chat data, people tend not to use spaces all the time. So there you need to figure out how to split words with spaces. I won't go into details here. And then you have entity recognition, so named entity recognition that you can use to enhance your text samples. After that, we come to very good way of approaching problems. It's called fine tuning. So as you must have used for computer vision problems, so it's quite fast, and it's not always better, but probably it can be better than normal ways, and why should we reinvent the wheel? So here you can see a problem that I did quite a while ago. So when I initialize the weights randomly, I don't see any kind of separation. So I have a binary problem. I don't see any kind of separation between the classes. When I use pre-trained weights, I can see like some of the samples start making small clusters together, and after fine-tuning, it was totally separable from each other. So here the AUC was like 0.9899 in that range, and it was so I was trying very different complicated methods, and then just trying one ImageNet, I got very good results. The next thing that you can do is hyperparameter tuning. So it becomes very difficult for neural networks because there are a lot of parameters. For light GVM, there are even more. So you can do some kind of grid search, some random search, or optimize by hand, some kind of Bayesian optimization. So grid searches, you have a grid of parameters and you just go through every combination of parameters there. A random search where you have a grid of parameters, but you search randomly. So you use parameters randomly. Bayesian optimization is something that you can do too. So I'm using a different boosting method here called catboost, and I define some kind of search space. So what I'm going to use here is scikit-opt. And so I define what are different iterations. Iterations can be integer, and let's say between 10 and 300, what kind of depth I want. Learning rate is a real number. So, and then you have different other parameters for catboost classifier. So once you have defined your search space, you can initialize bias search, cross-validation. You have a given classifier, which is catboost in our case, the search space. You define what kind of scoring you want to use. So here I've not shown the function, but you can always go to this link, and this provides you with everything that you need for hyperparameter optimization using scikit-opt. So after defining these parameters, you just run this, you just fit, and you will see like, okay, it's going through different values, and then in the end you probably have some kind of good parameters. But I basically tune by hand most of the time, and this is a list of different parameters that I have made that you should look at when tuning. So you can see like for XGBoost, you have a lot of different values. But for naive base, you don't have anything because there is not anything. So to end with, it's like to create a good machine learning pipeline, first steps are to understand the data or explore the data properly. Then you have pre-processing, feature engineering, feature selection, and all the nice things like good cross-validation, low error rate, post-processing of data if there is any, and some kind of chemical X, which is some secret sauce. And then in the end, you have a good machine learning model. So with this, I would like to end my presentation, and I'm up for any questions that you have.
Yeah, it's unmuted. Hi, Abhishek.
Hi.
I don't know whether I understood some of the line of codes. I think the visual cues are amazing.
Oh, okay. So yeah, I think I
No, I'm
made
just
it.
joking. It added a lot of laughter in the room, I can tell you.
Okay, thank you very much.
Okay, now are you able to open the Slido link? If you can put it on the screen so that we can see.
Sure. Just give me a second.
I've seen that if everything else fails, use XGBoost.
It's a secret of against energy.
So,
It was on the invite there, maybe.
yeah. Okay.
Okay, maybe you can pick. I don't know how you are doing on time. Maybe 10 minutes of you can choose the questions in the top to bottom order.
Sure. So the first question is how do you decide whether a problem is better solved with machine learning than other approaches?
Yeah.
What kind of other approaches are we talking about?
See, the question there was, should we use a simple statistics to solve a problem, or what happens today is everybody throws machine learning as just one way of solving. The question is, using traditional simple statistics, some problems could be solved. But when do you choose a machine learning approach to solve a problem?
Yeah, so it depends on the problem. So I would give you an example quite recently. It was yesterday. So a friend of mine asked me if problem uh, they're working in the industry and they want to solve one certain problem that they have using machine learning just for the sake of it. So, and when I asked about the data, they had 250 samples, and that's quite low for any kind of machine learning. Probably SVM will be nice, but so I always start with very simple approaches, and I think if simple approaches are performing quite good, if just certain combination of variables or statistical methods are also like basic building blocks of machine learning. So if you're getting quite good results using simple approaches, which are non-machine learning based, then it's probably better to just stick to it and not use machine learning just for the sake of using machine learning. So I would move to other question.
Yeah, please.
So define how do you learn and practice feature engineering? So to learn feature engineering um, is to get your hands dirty with different kinds of data. So what I usually do is I hi, can you hear me?
Yeah, we can hear you.
Okay, great. So yeah, to get your hands dirty. So if you're if you have time, then you should probably just go and solve some or look at some different kinds of data. So like what I usually do is like instead of going playing football or going outside, I just pick a problem in the evening when I'm back home from work, and from Kaggle or from different other competition websites, and then I try to perform some kind of exploration on data and see what kind of features I can generate. So like even when I was talking about Quora, the features that I was showing are right now what people will do is they're just going to use neural networks for that kind of problem, but you have to first learn the basics, and feature engineering becomes a little bit difficult if you don't have the domain knowledge. So in that case, you can create features based on your intuition, and the only way to see if feature is performing well is if it's improving the model. So yeah, I would say that. I think I got a new one. How do you deal with problems where data size is very minimal, but there's a lot of variety across the example? So yeah, when you have like very less amount of data, uh, if it's not images, I would go for something like SVM. If it's images, then 100 samples can easily be expanded to thousands of samples using augmentations. And uh, are you talking specifically about images or other kind of data?
Yeah, I think the question was data in general, images and
Okay.
not. Yeah.
So yeah, for 100 examples, there are many different ways. If it's images, then we should probably go for some kind of Siamese kind of approach where you compare a couple of images together. So in that, using that, you have thousands of samples. But if it's not images, then going for something very simple like linear regression or SVMs. SVMs will generalize quite well, small number of samples. So if you have less than 20,000 samples, you can always try SVMs, not go for something complicated. For neural network stuff, you will need a lot of different samples. So moving, does that answer your question?
Sorry? Yeah, okay, 1 second. I think you move on to the next question. The person has just gone out who had asked that question.
Okay.
Yeah.
So what does it take to make machine learning model adaptive? Adaptive is generalization or?
Yeah, see, the question again is that, many times the models are made which become actually a black box. It doesn't take into account the feedback into constant improvement and making it a better model every day. So, your suggestion on how do you design machine learning models which are actually adaptive, which has feedback loop into the system?
Okay, so yeah, this is something that I've discussed in my presentation today. So having a good cross-validation system is very important, first of all. And if you want to, if you want to train on incoming samples, then having a generator is very important. So you can keep on training the model and updating the weights if it's a neural network. Um, so if you're using models like random forest or boosting, then you have to keep training on all of new data plus the old data. So if you avoid using those kind of models in a real-time setting, it would be nice. Um, Using simpler models is sometimes very useful, simple approaches. And yeah, that's what I would say. The most important thing is cross-validation. If you have a good cross-validation system, then you should trust that, and it would perform well in a live setting or like even in competitions.
Got it. Nice. Maybe you can take last two questions, Abhishek.
Last ones?
In the sense, two more questions I said. Yeah, they're all
Okay.
right. Yeah. You can choose.
I can choose this one. Not to do things. I don't know if I have three of them, but uh, so these days people start their machine learning journey with some building their profile, and to build their profile, they want to tackle some problem, put it on their GitHub and everything. So when you're starting with a problem, it's good if you don't copy paste the solutions that you already have, but try to understand. So when I started with very basic, simple approaches. I was into image processing, and I started with a competition called facial expression recognition. where I built very simple models, like finding angle between eyes and nose and these kind of things. And then I was at the bottom somewhere, but I learned a lot from the solutions that were shared, and I tried to implement it on my own, reading papers. So these kind of things are very useful. It's also very important to learn if you're planning to go to industry. It's very important to learn not just to build very complicated models, because probably you won't even be able to use them in the live environment. So you have to take care of what kind of response time you get and all that kind of things. So learning in depth, I think, is something that you should do, and not do like copy pasting code. When the data set is small, use a VM. What is the difference between Kaggle and data science at work? So in Kaggle, you have clean data, and at work you don't have clean data. So the 70 to 80% time data scientist is spending at work is to gather the data, and very little amount of time building the machine learning model. So that's a huge difference. In Kaggle, we are fighting for the last 0.005%, but at work we don't do that. So probably if the small, the difference between a model ranked at number 1 and ranked at number 500 is probably nothing when it comes to real world. That's one of the differences.
Great, Abhishek. I think we've taken a fair amount of your time, and thank you very much for your time today. And I'm sure this is just the beginning. We will be having many more sessions the time to come. And I also would like to thank all the audience here, particularly our customers and also from academic institutes. People have come here, and thanks everyone. And have a great weekend, Abhishek.
Well, thank you very much for inviting me. I hope it was fun for you guys and something to learn.
No, absolutely. I think we have recorded it. We will rerun, and I'm sure it'll be a learning. It'll be in our knowledge base for reference.
Thank you very much.
Thank you.
See you. Bye.
Bye.